Okay, now we're going to be transforming the stiffness metrics that we found from local axis to global axis. Okay, so at first let me just take a pen. So here we have the transformation right over here. We have UA of the local axis. So this is going to be transforming the global axis. If you look at the picture here, this is UAL. So this is in this direction. So if I consider the vectors for this resultant force, if I consider UAL to be a resultant force, then the vectors are going to be UAG right over here, UAG and VAG, right? And if we consider the theta angle from this location to here, then UAG is going to have a cos theta component. So UAG is the cos theta component of UAL, and VAG is the sin theta component of UA local axis, right? So this is how we can write up the equation: UAG cos theta plus VAG sin theta. All right, now right after that we can see that there is no B point deflections here. So the B point deflections here can be just written off as 0 plus 0, no vertical B point deflection, no horizontal B point deflection. Right after that we have VAL. So this is VAL. If this is VAL, then the components of this are going to be an UAG in this location, in this side, UAG, and a VAG on the upward, right? Since this is on the leftward side, we're going to call this minus UAG. And since the theta angle was from here to here, this time the theta angle connects with VAG before it connects with UAG. That means this time VAG is going to have a cos theta component and UAG is going to have a sin theta component. So right here we have VAL equals to minus UAG sin theta plus VAG cos theta. And again, here UB has no part to play in it because this is the A point. So this is going to be 0 again plus 0. So this is our equation 7. Right after that, similarly, the way we formulate UAL and VAL in the global axis, we can formulate UBL and VBL similarly. If we look at the directions right over here, we can do it similarly. Just the thing is there are no A point deflections here, so this is going to be 0 for UA and also 0 for VA. Similarly here, 0 plus 0. Okay, before this we have 0 plus 0, before this we have 0 plus 0. Now, if you put the whole thing into matrix form, we're going to have, these are the local axis matrices. So this is the vector right over here, and this right here is now we can call this the transform matrix, because we have transformed the local axis matrix into the global axis matrix, right? And here are the zeros. You can see the zeros here that in the equation that were not written there. I just wrote them with the pen. And the zeros at the front, here we go, the zeros at the front that were not written, that were not typed here, I just wrote them with the pen. Okay, so we can say that this is the transformed matrix, and along with that we have to multiply this UA global and VA globals, so that is why it is right over here. So the U member, the deflection of the member, M stands for member, so the deflection of the member AB, we have a member here, this is the member AB. So the deflection of the member AB in local axis is equals to the transform matrix, this is the transform matrix, into the global member deflection vector. There you go, and this is the local member deflection vector. So the local member deflection vector is equals to transform matrix into the global member deflection vector. Okay, so this is what we're getting from here, and this is our equation 10. Okay, all right, so let's leave it at here, and we're going to continue on from here in the next lecture. Thank you very much for watching.